Welcome to this class. In this module we will see the other applications of the operation amplifier. So, this topic I thought that it will be interesting for you to understand, and that is about the multi-vibrator. So, how op amp can be used as a multi-vibrator. So, when we talk about operation amplifier, one important thing that we have learned is its characteristics as a comparator. So, how exactly op amp can be used as a comparator, you know, right, it is very simple circuit. So, when you want to design op amp as a comparator, and from comparator to a multi vibrator, right, how we can design it. So, this topic, this module is for understanding how multi vibrator can be designed. We will see how multi vibrator we can design using the breadboard and 3 of our favorite equipment, starting from your DC power supply. We will have function generator and we will have oscilloscope. Of course, we will have breadboard or op amp and few components, 2 resistors which is a passive component, and we will apply sine wave and look at the signal which will be a square wave, and you will see how the hysteresis happens and how this comparator acts as a multi vibrator. So, let us see how the multi vibrators can be designed. When we talk about operation amplifier and comparator with positive feedback. So, what will happen if an op amp comparator with positive feedback is designed, alright. So, first we have seen how the op amp can be configured to operate as a comparators, we have already seen that, right, in their open loop gain, open loop mode. That means, we just draw a op amp, we use here, right, we have applied bias plus minus, now you already know, right, and we have seen that if the inverting terminal is let us say 2 volt, non-inverting terminal is 1 volt, then output will go to negative saturation, right. And if my inverting input is 1 volt and non-inverting input is 2 volts, that means my non-inverting input is higher than inverting input, my output will go to positive saturation. This is open loop, right. Now, if I apply positive feedback, then what will happen, right. So, what is that? The above configuration is fine, that means this configuration is fine. However, if the input signal varies rapidly or is not too noisy. Only this is fine when your input signal varies rapidly and is not too noisy, you see. So, that is very important, right. If input signal is too noisy, we cannot use op amp in open loop configuration. So, if the input signal V in is slow to change or electrical noise is present, then the op amp comparator may oscillate, switching its output back and forth between 2 level saturation, 2 saturation states, which states plus VCC and minus VCC, as the input signal hovers over the reference voltage V reference level, correct. So, that means that if I have input is low or noise is present, then the op amp will start oscillating and output will be between positive and negative saturation. So, a way to overcome this problem, is to avoid op amp from oscillating, right. This is the answer, but how we can avoid the op amp from oscillating, because we know that if the input signal is noisy, it will start oscillating. So, how we can avoid the op amp how we can avoid this problem, that is to avoid the op amp from oscillating. So, the solution is we provide a positive feedback around the comparator, So, what will happen? This feedback will be provided via a potential divider. We will see the circuit set up by 2 resistors from the output terminal back into the positive terminal, of the op amp. This is how we will provide the feedback. We will use a potential divider circuit, which you already know, there are 2 resistors, and we will apply the voltage across the potential divider circuit back to the positive terminal of the op amp, that is back to the non-inverting terminal of the operation amplifier. Once we do that, the use of positive feedback around the op amp comparator means that once the output is triggered into saturation at either level, there must be a significant change to input signal V in before output switches back to its original saturation point. What does that mean? That if I apply positive feedback, if the output is triggered to negative or positive saturation, right, I will have to overcome this negative and positive saturation values, then and then only I can switch back its characteristics. Otherwise, what will happen? The once output is triggered in saturation either level, there must be significant change to the input signal before output switches back to original saturation point. Otherwise, it will just be within the saturation region. We will see these things. We will see this thing in the experiment. So, we will know better what we are talking about, right. The difference between two switching points is called hysteresis, that will it will switch between positive and negative. It will go here, it will come back here, right, like this you will see the signal, and let us say this is positive saturation, this is negative saturation. So, the op amp will oscillate between these 2 points, right, and this is nothing but your hysteresis producing what is commonly called Schmitt trigger circuit. So, the multivibrator is also called a Schmitt trigger circuit. Alright. So, if somebody asks you what is the difference between multivibrator and Schmitt trigger, it is same thing, it is same thing. Yes, how we can design the multivibrator, you can always say that we can apply positive feedback to the comparator using the potential divider. Alright. So, it is easy, so do not worry about it, right. Now, let us see the functionality of the operational amplifier in its inverting configuration. So, inverting configuration we will use the op amp, and we will see how the hysteresis can be generated. Okay. So, the configuration we can see this configuration, right. We have whatever, see this V in is a input signal, V reference is a reference voltage, whatever is the voltage here, the signal that is given is half is R2 by R1 plus R2, that is half of V out. If R1 and R2 are same, it will be half of V out. What does it mean? The input here is fed using R1 and R2, right, output of V out and R2 by R1, that means that R2 by R1 plus R2 into V out is my V reference voltage, For R1 equals to R2, V reference voltage is nothing but half times V out, right. So, always remember this will be half times your V out. Now, if my V out is positive saturation, suppose V out is positive saturation, positive is plus 15, negative is minus 15, right. Then here it will be 7.5 volts, right. If my V out is negative saturation, here it will be minus 7.5 volts. So, my input signal should exceed this value, then and then only I will see the change. My input signal should exceed this value, otherwise it will remain in this particular condition, right. So, let us see whatever I have told here, whether it makes sense from the text or not. Let us see. So, what you can see, V in is applied to the inverting input of the op amp, resistors R1 and R2 form a voltage divider network across the comparator providing positive feedback, right. It is providing a positive feedback with a part of output voltage appearing at the input. The amount of feedback determined by resistive ratio is given by beta R1 by R1 plus R2. You can say R1 plus R1 by R2 because we are taking voltage across this point. We can both R1 and R2 are same, so it does not matter because it will be half times your output voltage if I want to give the input, if I want to calculate the V reference voltage. So, anyway, point is when the input signal is less than the reference voltage, that is V in is less than reference voltage, the output voltage will be high. You see here output voltage would be high when V in is less than V reference. The output voltage will be high, that is VOH, and equal to positive saturation value. It will be here when V in is less than V reference voltage. Why? Because the positive is higher than the negative, that means it will go to the positive saturation comparator, correct. So, as the output is high and positive, the value of the reference voltage on the non inverting input will be equal to plus beta or upper trip off value. That means that if I have positive saturation, that means here is 15 plus 15 volts positive, right. So, my reference voltage would be plus 7.5 volts, that is what it means, alright. and this is nothing but my upper trip point. I have to exceed this value here, then only I can change the signal, that means my V in should exceed 7.5 volts to see the change in the output, alright. So, as the input signal V in increases, it becomes equal to upper trip point value VUTP at the non inverting input. This causes the comparator output to change state, becoming low, VOL equal to negative saturation value as before. That means that when I will reach this condition, initially is this condition, right, V in is less than reference, then in that case I have positive saturation, means my reference voltage is plus 7.5 volt. Now, I keep on increasing V in voltage such that it increases, it gets greater than 7.5 volts. When it gets greater than 7.5 volts, then what will happen, that the negative here it will be, let us say 7.6 volts, alright. In that case, you see 7.6 is greater than 7.5, yes. So, what will happen? My inverting voltage at inverting terminal is higher than the voltage at non inverting terminal, which is 7.5, hence my output will go back to the negative saturation value, and my output will be minus 15 volts, right. So, minus 15 volts will create the reference voltage of minus 7.5 volts. Now, until and unless my V in is less than minus 7.5 volts, it will not change the signal, it will not, the output will remain at the low level, right. So, now it is at low level, again if I want to go to high level, it should exceed this value, which is minus 7.5 volts. Easy, extremely easy, right. Same comparator, but here you are triggering from in high to low, low to high, right. It is also called a Schmitt trigger. Okay. So, let us see further, but this time the difference is a second trip point value voltage created because of negative voltage appears as non inverting input. The same thing what we are talking about, right. Then the input signal must be now fall below the second voltage called low trip point or LTP for the comparator's output change or switch back to its original positive stage. Same thing what we have discussed is again here, right. So, what we have to understand is when V in is less than V reference, my output voltage is plus 15 volts and V reference voltage would be plus 7.5 volts. Okay. When my V in is greater than V reference, my output voltage will be minus 15 volts and my V reference would be minus 7.5 volts. Okay. Now, I have V reference 7.5, I have V reference minus 7.5. That means, if my V in is 6.5 or let us say 7 volts, my V reference voltage is 7.5 volts, my output will stay in positive saturation, that is positive 15 volts, alright. When this exceeds 7.5 volts, that means it goes to let us say 7.6 volts, my output will go to negative saturation minus 15 volts and this will become minus 7.5 volts. Now, to again change the output from negative to positive saturation, this voltage should be less than this voltage, that means it should be minus 7.6 volts. If minus 7.6 volt happens, then again this will be positive saturation, alright. This is how it works, so on off, and we defined upper trip limit, lower trip off limit, alright. The difference between two trip points is called hysteresis. So, what is hysteresis? Now, you can design that the difference between the upper trip point and the lower trip point in this particular case is called hysteresis, Here you see this one, this is your hysteresis, okay. Very easy, extremely easy, super easy. Now, everything for you becomes super easy because you already know how to use the operation amplifier, as various applications, right. So, when I talk about comparator, immediately your brain works that yes, comparator very easy, my inverting higher than non-inverting, output is my negative saturation, in non-inverting higher than inverting, output is positive saturation, R1 R2 is there, what else divider, R2 by R1 plus R2 or R1 divided by R1 plus R2, right. If R1 equals to R2 is half times V out, so easy. What is hysteresis, now you know, what is upper trip point, what is lower trip point, you know, right. So, for positive output voltages, V reference is beta into VCC, for negative output voltages V reference equals to minus beta into VCC. So, hysteresis is nothing but V out VUTP minus VLTP. So, what is VUTP? VUTP is beta into VCC minus of beta into VCC is nothing but beta into VCC plus beta into VCC equals to 2 times beta into VCC. This is what you got here, this is what you got here, easy, extremely easy, right. This is how you create op-amp comparator with hysteresis using the inverting configuration. Now, to design the circuit using multisim, again we will ask our friend Sitaram who will show us how to perform the experiment using multisim.
So, in this module we are going to discuss about a Schmitt trigger, how to implement a Schmitt trigger using operational amplifier by making use of TI board. So, here we have TI board. Basically this board contains all the op amps required for that. I will keep it here so that you can easily see the board. So, if you observe the TI board, it contains different subsystems starting from LDO regulator, DC-DC converter, transistors if you want to replace some transistor, and if you want to make use of a transistor in your circuit, you can connect it here. And it also has an input main power. So, once we give input to this main power, it will be automatically powered all the operational amplifiers and all the circuits that we have used, or all the subsystems that are there in the boards. So, it has other subsystems too, like in case if you want to place some diodes in your circuit, you can make use of the subsystem of diodes here, trimmers as well as analog multipliers. So, along with these subsystems, it also has an inverting type as well as a non-inverting type, or as well as a basic op-amp type subsystems too. So, right now in this module we are going to use op-amp type 3 basic one. So, in this subsystem they are using TL082. So, as the name itself we can see that TL082, it is a TI based operational amplifier. It contains 2 op amps inside, that means it is a dual channel op amp. And when you observe here, one set of op amp you can see on the top side here, one set of op amp we can see on the top side, and another set of op amp we can see on the bottom. So, depend upon our experiment, we either use either the top one or the bottom one. When you closely observe this board, in case if you want to connect some external resistors or any other external component, this board can also provided an option with a smaller breadboard. It is also similar to our normal as usual regular breadboards, but it is a smaller in size, so that any external which is not available in the board, like your resistors which are not available in that, or your other kind of transistors or anything, can be connected and wired through this using any kind of jumpers. So, right now by using this board and by using this particular subsystem module, we are going to see how analog using an op amp, how inverting Schmitt trigger can be implemented. So, when we look into the slide, so as we have seen in the class, so this is an inverting type of Schmitt trigger. I hope by this time you would have understood why it is called inverting type of Schmitt trigger. The reason is input is directly connected to your negative terminal of your op amp, and as we have seen, the difference between a Schmitt trigger and your normal negative feedback operational amplifier, that means when you are using op amp as an amplifier, the major difference is that in case of an operational amplifier using as an amplifier, the feedback will be connected to the negative. So, that is called a negative feedback, but whereas in case of Schmitt trigger you can see the feedback is positive. So, as we know that the op amp open loop gain itself is very higher, when you connect in a positive feedback, the overall gain of the system will be even more higher, as we have already seen in the class. So, that is the reason the op amp will always be in a stage of saturation, will always be oscillate in saturation stage, but when it oscillates, when it goes to plus VCC, when it goes to minus VCC, that entirely depends upon the resistors R1 and R2 that we choose, and depends upon the VSS and minus VSS that we choose. So, in this we will see a brief understanding on inverting type of Schmitt trigger circuit and simulation of this inverting type of Schmitt trigger circuit, and once the simulation is done, the results will be compared with the op amp circuit built using a TI board. So, as we know that the op amp V naught output voltage can be written as minus A naught into Vi minus beta into V naught, where the beta is nothing but here R1 divided by R1 plus R2. So, the value of the beta depends upon the resistors R1 and R2 that we choose. So, this is responsible, or the values of R1 and R2 are responsible to decide what thresholds to be used for your circuit. So, as we have already discussed, as we have already seen in our professor's lecture, that the relation between the thresholds depends upon beta value. So, what is beta? So, beta is related with the resistance that we have choose. It is nothing but R1 divided by R1 plus R2. So, beta into minus VSS is our lower threshold value, and beta into plus VSS is our higher threshold value. So, how the output is related to the input? So, when we look into the characteristics curve or the relation between the input and output, we can understand that as my input is keep on decreasing to minus beta VSS. So, once it reaches to minus beta VSS, the value will become plus VSS. Since it is inverting, when the input voltage is lower than the lower threshold value, then the output will become higher, that we can see here. Similarly, when the input is greater than beta VSS, then the output becomes lower. So, lower in this case is nothing but minus VSS. So, it will always shift from plus VSS to minus VSS, or from minus VSS to plus VSS, but that depends upon two thresholds. That threshold entirely depends upon the beta value and VCC, plus VCC and minus VCC, that is nothing but the power supplies that we are giving it to an op amp to operate it. So, when we look into the circuit, and the procedure that we follow in order to do the experiment on a Schmitt trigger. So, we will be connecting the circuit in the same fashion. So, before connecting it, we will also see the simulation by connecting the same thing. So, in order to do the simulation, let us consider few different resistance value, and we will see the theoretical value of the beta with the values of resistance that we have considered, as well as the hysteresis width, and where exactly what is nothing but a lower threshold value in this case, and what is a higher threshold value. So, for that, let us consider different resistance value. Now, first one I will consider R1 as 1 kilo, R2 as 10 kilo. So, as we know that beta, the relation between R1 and R2 is beta is equal to R1 by R1 plus R2. So, it is nothing but 1 divided by 11k. 1k divided by 11k. Now, what is the value of 1 divided by 11k? So, we will see the value. So, 1k divided by 11k. So, k cancel. So, the beta is nothing but 0.09. That is our beta value. Now, so the lower threshold VTL I am considering it is nothing but minus beta into VSS, which is nothing but 0.09 into minus 15. So, 0.09 into minus 15 when we calculate it. So, again we will go to calci 0.09 into 15 1.35. So, why 15? Because I am going to use plus VCC and minus VCC as 15 volts and minus 15 volts. So, R1 initially I will be considering 1K and R2 as 10K. Similarly, this is minus this is a lower threshold. What about the higher threshold? So, it is nothing but beta into VSS, which is nothing but plus 1.35. This is minus 1.35, this is plus 1.35. So, I will rewrite this once again. So, these are the threshold, we will see in simulation. So, next we will consider other two values too. Let us take R1 as 10K, R2 as 10K. So, what will be the value beta? It is nothing but 10 by 20. So, which is 0.5. So, VTL lower threshold value will be minus beta into VSS, which is 0.5 into minus 15, 7.5, and VTH is plus 7.5 volts, is not it? These are our higher and lower threshold values. Then we will also see for other resistance values too. R1 as 1K and R2 as 2.2K. R2 as 2.2K. So, then beta will be 1K divided by 1 plus 2.2, 3.2K. So, when we calculate 1 divided by 3.2, it is nothing but 0.3125. 0.3125 is our beta value. Then what about VTL? It is nothing but minus 0.3125 into 15. So, it is nothing but 15 into 0.3125, right, 4.6875 approximately 4.7 or 4.6875, and higher threshold value is 4 plus 4.6875 volts, right. So, what do you mean by hysteresis width? When we look into the previous one, this is nothing but our hysteresis width, the difference between the lower threshold and our higher threshold. So, when we see that in this case 1.35 plus 1.35, 7.5 and 7.5, 4.6875 and plus 4.6875, those will be the hysteresis width. Now, we will verify the same thing with our simulation, then we will verify with our TI board too. So, let me go back to the simulation. We will look into the multisim, as we have already seen about the multisim in the previous sessions too. So, once again I just repeat, this is an multisim online circuit simulation builder software. So, here if you observe on the left side, we have a different modules that we can place on this circuit board. So, starting with analysis and annotation. So, where if you want to measure voltage or if you want to measure current, both voltage and current, and if you want to connect any ground references points, and different types of sources, okay, different types of voltage sources here we can see, and resistors in case if you want to replace resistors, capacitors, inductors, potentiometers, fuses, everything, and operational amplifiers 3 op amp base, 5 op amp base, like and normal 741 3 to 4 op amps, basic op amps, diodes, transistors and indicators, everything. So, whichever we require, we can place it on the circuit board, we can connect the circuit whatever we have seen before connecting it on a breadboard, and we can visualize the response of the circuit using the grapher. Now, we will connect the same circuit that we have used, that we are going to verify the working of the circuit in our multisim. So, first one is I have to take an op amp I am going to take 5 terminal op amp, I am placing 5 terminal op amp here, right. So, since it is an inverting type of op amp, so what I will do is to just match with our circuit connections, I am swapping it. Now, if I see this is the negative and this is the positive terminal. So, since I have to power it, I will take a DC voltage source, I will place it here. Now, this value should be 15 volts, right. So, since the negative terminal is connecting it to the negative terminal, observe here the negative is connecting it to the negative. So, even though it shows a 15, it is nothing but a minus 15 volts is connected here, right, and I have to connect a ground. So, I am taking a ground and connecting it here. So, negative supply is done. So, what about positive supply? Yes, we also have to give plus 15. So, plus 15 should be connected here. I am connecting plus 15 here. Since the default is 12, I am changing it to 15 because we are using 15 volts power supply in this case, and the other terminal is ground. So, the plus VCC and minus VCC connections for our op amp is done. Now, next thing is we have to take a resistors, connect it. So, we know that since it is an inverting Schmitt trigger, right, it should always be a positive feedback. So, I am connecting one resistor to the positive terminal, one more resistor should be positive feedback from here to here. And where is the input to be connected? Since it is an inverting Schmitt trigger, input should always connect it to the negative terminal, right. So, I am connecting input to the negative terminal and other terminal of the source should be grounded. Right. And what about this terminal? Other terminal of the resistor? It should be grounded, right. So, ground, taking ground and I am connecting. So, does it look similar to our circuit that we have seen in our slide? See, positive voltage to be connected to the negative terminal and R1 should be connected to the positive, right. So, we can see here, right. So, R1, but resistance values. So, one should be R1 should be 1 K, R2 should be 10 K. So, this I will change it to 10 K. Clear? Now we have to compare input and output. So, in order to see the input signal as well as an output signal, we have to connect oscilloscope to that. So, I will take voltage probes for the analysis purpose and I will be connecting one to the input. So, the green indicates the input signal that is being connected to this, and I will take one more probe, I will connect it at the output side. So, the blue indicates the output signal. Now, what is the value, input voltage value that we have to apply to the system in order to see the change in the output? So, since the thresholds that we set, the resistance that we have set is 1 K and 10 K, for that resistances the threshold value is nothing but 0.09 and the threshold voltage is minus 1.35. So, in order to see that change, the input voltage should be higher than the threshold values, isn't it? So, for that reason what I will do is that I will take peak value as 2 volts. So, peak to peak is 4 volts. So, that we can see the change. Now, once the circuit is done, let me save the circuit, save, and this is nothing but inverting Schmitt trigger. Okay, inverting Schmitt trigger. Okay, I am saving it. So, I will go to the grapher, let me run the circuit, right. We got a signal, but if you observe the signal, we have two things in the same CR in our grapher. One is the green color, other one is the blue color. So, the green color indicates our input signal, whereas the blue color indicates our output signal, isn't it? Now, how do we understand whether at what time it is switching on, at what time it is switching off? When we recall what we have discussed in the Schmidt trigger, or what professor has discussed in the inverting Schmidt trigger time, we know that when the input signal is greater than higher threshold value, then output should be minus VCC. Similarly, when the input signal is lower than lower threshold value, the output will be plus VCC. Since in our case plus VCC and minus VCC are plus 15 and minus 15 volts, you can see the change from plus 15 to minus 15. But whether it is switching happen at the lower threshold or the higher threshold, that we have to see. For that reason, what I will do is that I will create a cursors. I will create a cursors, and for our easy to understand, I will also increase the time division. So, it is nothing but a zooming. I am increasing the time division. So, we can see, and I will create a cursor, x axis cursor. Now, observe. Now, we will move the cursor. We can notice here cursor 1, what is at what input voltage it is at. So, we when we look into the threshold values, threshold is nothing but 1.35 volts. So, if my input is greater than 1.35, then it should go to minus VCC, isn't it? Now, slowly move towards 1.35, right. So, somewhere close to 1.34, we can see that it is going to minus VCC, right. Now, another thing is, when the input is greater than 1.35, then the output should be plus VCC, just observe. So, I will be keep on moving, or I will take another cursor, we can visualize it in cursor 2 here. So, slowly move and observe this minus 1.35, right. Then it is initiated to plus VCC, right, it is clear. Now, we will also see, for another set of resistance values, what is that, 10K and 10K. So, 10K. So, I will change the resistance value to be 10K now, right. So, I will now, what is happening here? When we observe that, when we look into only the grapher, I can only see plus 15. I mean, I cannot see any change in the pulses. I cannot see any pulses. The reason is that the input voltage, when we look into the higher threshold and lower threshold values, right, the higher threshold value is 7.5, lower threshold value is minus 7.5. But what about my input? Input is lower than the threshold value. That is the reason we can only see one output VCC. So, in order to see the effect of the system, effect of our circuit, the thing is we will change our input peak value to higher than our higher threshold value. So, what I will do? I will go to somewhere around 10 volts. Peak value is 10 volts, that means peak to peak is 20 volts. Now, when we see, yes, we observed it. So, I will make it as single. So, then go to the grapher, I will go to the settings, I will increase a little bit. Okay. Now, here we observe. So, what are the thresholds now? 7.5, minus 7.5 and plus 7.5. So, that means when the input signal is greater than higher threshold value, in this case is 7.5, the output should be minus VCC, that means minus 15 volts. And if the input is lower than 7.5 volts, that means lower than minus 7.5, that is our lower threshold value, the output should be plus VCC, that means output should be plus 15. Let us observe. So, I will move the cursor towards minus VCC, minus 7.5, sorry, lower threshold value, I can, it is almost close to, minus 7.3, right, 7.58, I can see the cursor 1. So, it is going towards plus VCC, right. So, which is similar to what we have discussed. Then I will take this one. I will move closely towards more than plus VCC, meaning the higher threshold value plus 7.75. Observe here, this is somewhere around 8 volts. So, I will move towards 7.5, 7.6, 7.47, approximately 7.5. We can see that whenever the input is higher than the 7.5, we can see it is moving towards our minus VCC, which means that it is acting as whatever we have expected. Now, we look for other settings too. So, other resistance value that we choose is one is 1 k, other one is 2.2 k. This is 1 k. So, I will change it to 1 k and this should be 2.2 k, 2.2 k. Now, what are the thresholds? Higher threshold is 4.6875, lower threshold is minus 4.6875, meaning when we look into the circuit, how should it work? The circuit should work like when the input voltage is greater than 4.6875, the output should be minus VCC, meaning minus 15 volts, and when the input is lower than minus 4.6875, the output should be plus VCC, meaning plus 15. Now, what I will do? I will move my cursor towards 4867, minus 4.6875. So, I am closely moving to somewhere related to 4.6875, yeah, 4.69, so approximately equal to that. I can see when the input is higher going to lower than this particular threshold value, the output is going towards plus 15 volts. Similarly, when I move towards positive higher threshold, somewhere here you can observe cursor to 4.3032. So, I have to little increase 469, sorry, 4. Yeah, somewhere around 4.7 approximately. I can see that when the input is higher than that higher threshold value, so the output is minus VCC. So, I will put using y axis cursors, right, we can see the thresholds too, 4.6875, right. So, 4.6875, yes, 4.68 minus 4.68. Yes. So, this is the C1, whichever, if you notice here, this C1 is nothing but our higher threshold value. So, we can clearly see that when the input voltage, this green color line, is greater than the C1 value, this higher threshold, this is going to, the output is going to minus VCC. When the input is lower than C2, which is nothing but our lower threshold value, minus 4.68, the output is going to plus VCC. Now, in realistic way, where we use such kind of a triggers? Imagine, for example, like say, imagine I have an water heater and I want to switch on at one particular temperature, but I should be switched off at another particular temperature. It should not be below the same temperature. When you observe the difference between a comparator and a Schmitt trigger, we can see some lag between the switching on and switching off. It is not at the same time. Whereas in case of a comparator, if the input is higher than that particular threshold, it will on. If it is lower than that same threshold value, it will off. But in this case, it is not like that. When the input is greater than one particular threshold, it is going to low, and when the input is lower than the threshold, that threshold, it is not going to high. But in order to make it high, the input should be even lower than the first threshold value, only then it goes to the high, right. So, this is how this is the difference between the inverting Schmitt trigger and a comparator, right. Now, we will see by connecting the same circuit using the TA board, and we will see whether the experimental results are matching with the simulation as well as our theoretical calculations too. Now, when we look into the board, as we have already seen the complete the board, how it looks like everything in our last sessions. So, we are going to use only this particular part, which is op amp basic type. So, this board contains TL082, as we have already know that this is a dual op amp. So, within this single IC it has two op amps, one op amp is at this point, other op amp connectors are at this point. Now the powering is done by using this connector here. The powering is done using this connector. So, since we are using plus VCC and minus VCC as plus 15 and minus 15, we are using the power supply, we are using this power supply channels, which is the red one is plus 15, the green one is minus 15, and this is the ground terminal, the black one we can see here, the black one is the ground. So, using these wires, the red is connected to plus 15, the black is connected to minus 15 and the white is connected to the ground. So, we are connecting in the same way. Here if you observe, the red is connected to the positive supply. So, since it is connected here, all the op amps are powered with the same VCC, and the black is connected to the negative value here. We can see here this is a negative, right, and the white one is connected to the ground, right. We can clearly see here. That means the op amps right now it is working with plus 15 and minus 15 volts. Since the op amp can power by even slightly more than plus or minus 15 volts. So, we are using plus 15 and minus 15 because even in our simulation and even in our theoretical calculations of higher threshold and lower threshold, we have used plus 15 and minus 15. Now, what we do is that we will use this particular portion of the op amp, and this particular portion does not contain any resistors, but we require resistance, isn't it. So, what we do is that we use this breadboard to connect those resistance value. So, what are resistance that we have used? 1K, 10K and 2.2K. So, using this breadboard we will connect the resistance and we will wire it using the jumpers. So, when we see this op amp, the negative terminal is the top one, the positive terminal is the bottom one, right, and the negative terminal has some Burr connectors. So, using the jumpers we can wire from this Burr connectors to our breadboard, and when we see even the positive terminal we have another Burr connectors, even using this we can wire it. Then the bottom one is already grounded, whenever we require a ground we can take directly from here, right, and output we can see here, this is our output, and we do not have to connect any plus VCC and minus VCC here, since we have powered it at that particular at the main power source. Now we will take resistors, we will take a jumper wise and we will connect it. So, first one we will use R1 as 1K, R2 as 10K, right. Okay. So, we will use R1 as 1K and R2 as 10K. So, how do we connect it? The negative terminal has to be connected with function generator. So, if you observe here, this is our function generator, these are our function generator probes. So, the resistance now we are using is 1 kilo and 10 kilo, and we are using a function generator, to provide the required signal. So, what signal that we use, what are the thresholds? If you remember, it is lower threshold is minus 1.35 volts and higher threshold is 1.35. Now, we have to put our input signal higher than the positive and the negative threshold values. So, we will set in this function generator. So, the peak value should be more than 1.35. So, we will take 2 volts. In the simulation we have taken peak to peak of 4 volts, our peak value is 2 volts. So, frequency of 100 hertz we will take. So, we will go to amplitude and the peak value peak to peak how much we set? 4. So, we will set the value as 4 peak to peak, right. So, input voltage is greater than our threshold values. So, now we will switch on. So, we will switch on the supply. So, this starts giving us the input value. Now, this has to be connected to where? We should connect it to the negative terminal. This we should be connected to a negative terminal. Now, when we look into the board, so which is a negative terminal at this point? This particular portion is the negative connector. So, we will be connecting to this point, right. So, this input is connected to this. In order to visualize both the input and output from the CRO, one connector from the CRO. So, in order to visualize our input signal, what we do is one channel of the CRO is again connecting it to the channel of the CRO is connecting it to the input. So, here we can see this is connected, one channel is connected to input here. Now the grounds of the both should be shorted. So, what we do is that, so we will use in a breadboard. So, the grounds everything will connect it to the negative terminal here. So, negative is ground for us. So, all grounds we can common it. So, we are connecting to ground. Then we have to connect R1 and R2 resistors. So, we will take 1K resistor and 10K resistance. So, now we are taking a 1K resistor and that should be connected. This is 1K is nothing but our R1. So, this should be connected between positive terminal and the ground. So, if you observe here, the one lead of the resistor is connected to the negative, here, and other lead of a resistor we are going to connect it to the positive terminal of op amp. So, positive terminal of op amp is this particular point. So, to the positive terminal, to the resistor. Other part is we have to connect a feedback resistor. So, feedback resistance is 10 kilo. So, we will take 10 kilo. So, 10 kilo should be connected across positive terminal and output voltage. So, if you observe, the one terminal of 10 kilo is connected to the junction point, right. Here we can see the junction point. This junction point is nothing but this junction is connected to the positive terminal of op amp. The other terminal of op amp we are going to connect it to the output voltage. So, we will use one more jumper and so this is our output, this is being connected to the other terminal of resistor, right, clear. Now the ground should be connected. So, we will take one more jumper, the ground from here will be shorted to this particular ground. So, that everything will be at same point. So, take ground and to ground. Right, circuit is clear. So, what we have done, the input is connected to the negative terminal, since it is an inverting Schmitt trigger, input is connected to the negative terminal as well as CRO first CRO probe is also connected to the negative terminal, and R1 resistor is connected across positive terminal of op amp to the ground, right. The ground is also connected to the ground terminal that we can see here, yes, and R2 resistor is connected in the feedback, that means across positive terminal of an op amp and the output voltage. In order to visualize an output, we will take another CRO probe, we will take other CRO probe and we will be connecting it to output voltage. Other terminal of CRO probe will be connected to ground, right. So, we will switch on CRO, function generator is already switched on. Let me switch on CRO. So, this yellow is input and the blue is output. We can see whatever the signal that is coming from our function generator will be in yellow in color, the output received from the op amp voltage will be in blue in color. Now, so if we see here, we made all the connections now and input is also connected to the negative terminal, out and CRO is also connected to the negative terminal, that is nothing but from the source, and output is also connected, another channel of CRO is connected to the output of operation amplifier. So, when we look into the CRO output, we can see here the yellow represents our input, right. This is our input and the blue represents our output value. Now, what are the thresholds? Since the resistor that we have used is 1K and 10K, the thresholds are 1.35 is a higher threshold value and the lower threshold is minus 1.35. So, when the input is greater than higher threshold, the output should be plus minus VCC. Since it is in inverting, it will be always ulta, inverting. So, I will create a cursor here and I will make channel 1 cursor and I will take amplitude, okay, I will take time and here the cursor 1, I will select the cursor, I selected the cursor 1, here we can see, and when you see the cursor 1 reading, I will take any one of the peak, any one of the value, I will move slowly towards 1.35. So, right now it is at 7 volt, I will decrease to, now it is at 2 volts. Right, now 3.6, 1, 1, 2, 1.8, 1.4. So, when we see that, or what we can do is that we can create, since it is very difficult to tune here, we can create voltage thresholds as we have seen in our simulation too. So, I will go to the cursors, rather than taking an time, I will make it as amplitude cursors. So, one I will set it to the voltage, when you see the cursor 1, it should be plus 1.35, I will make it as 1.35. So, approximately as 1.4 and cursor 2, I will go to the cursor 2, I will make it as minus 1.35, approximately 1.4 or 1.2. So, when we see that I have already created 2 cursors, right, and when we look into this particular portion, this is one threshold and the bottom one is the another threshold value. So, whenever the input signal is greater than this particular, see here, this is first threshold. So, I will go to the channel 1, yeah, the dark yellow one, the first yellow one is the first threshold, the bottom yellow one is the other threshold. Now, when the input yellow line, the sinusoidal wave is greater than this threshold, the output is going to minus VCC, right. Now, when it is going to positive VCC, it is going to plus VCC only when the input is lower than the lower threshold value, right. So, it is clear that it is following as per our theoretical as well as our simulation too. Now, we look into the other resistance value. So, other resistance what we have taken? We have taken 10K and 10K. So, when we look into the board, now we have right now the circuit is connected with 1K and 10K. We will replace this 1K resistor when we see this is 1K resistor which is connected to ground and reference, we will replace 1K resistor. So, before replacing it we will be switching off the power supply. So, connecting across ground and negative terminal, right, because the feedback resistor is already 10 kilo ohm resistance. Now, we have connected 10K, both 10K resistors, right, as one has input, one is input R1 resistance and other one is a feedback resistance. Now, let me switch on the circuit. I just switched on the circuit. Now, what are the thresholds now? It is nothing but beta into VCC. Beta is R1 by R1 plus R2. So, which is nothing but 1 by 2, 7.5 into, sorry, 0.5 into 15 volts, it is 7.5. So, the higher threshold is 7.5, lower threshold is minus 7.5. So, the output will become higher only when the input signal is lower than the lower threshold value, whereas that means when the input signal is greater than 7.5, it will become minus VCC. When the input is lower than minus 7.5, it will become plus VCC, and that is what we have also seen in our simulation too. Now, we will look into the CRO, how the signal is up, right. Now, when we look into that, so we have to change our cursors, because this is the cursors are placed based upon the previous values, previous resistance value. Now, when I move the cursor towards, when you look into the cursor 1, right now the value is at somewhere around 2.2, I will move towards 7.5, positive 7.5, 6, 6.8, 7, 7.4, I am making it to 7.4. So, because it is very hard to make it 7.5 in this, and again I will go to the cursor 2. So, cursor 2 I will make it as minus 7.5. Oh, it is going positive. So, I will move it down, Now, right now it is at minus 8.6, slowly coming up, minus 7.4. So, we can see cursor 1 is connected to 7.4, cursor 2 is connected to minus 7.4. So, this is cursor 1, the top yellow line, we can see here, this top yellow line is cursor 1, the bottom yellow line is cursor 2, right. So, here we can easily see that when the input signals, input sinusoidal signal, this line, right, when the input sinusoidal signal is greater than the first cursor, the output is going to minus VCC, and the input sinusoidal signal is lower than the lower threshold value, the output is becoming plus VCC, right, which is also similar what we have seen. Now, we will take 1K and 2.2K. So, the values of our thresholds are minus 4.6875 and plus 4.6875. So, when we look into the board, we will switch off the power supply once. So, the output is becoming 0. When we focus on the board, we can see replacing of 10K with, so 10K resistor is the feedback resistor. So, R1 is 1K resistor and R2 is 2.2. So, both the resistors has to be changed. So, now we are connecting R1 which is 2.2, sorry, R1 is 1 kilo. So, we are connecting 1 kilo across ground and positive input terminal, and the feedback resistor is replaced with 2.2K. So, the beta value will become 1 kilo divided by 3.2K, which is 0.3125, right, and higher threshold and lower thresholds are 4.687 and minus 4.687. So, how does it work? When the input voltage is greater than plus 4.6875, the output should be minus VCC, and again when the input is lower than minus 4.6875, then the output will become plus VCC. Now, when we look into the CRO, the connections are done. When we look into the CRO, we can see here that now we have to replace our cursor points. Now, what we do is we will go to the cursor 1, we will make it as 4.68. So, right now it is at 6, 5.2, so 4.8. So, the cursor 1, this yellow line is at 4.6, 4.8. So, we need 4.6, right. So, 4.6 I mode. Then I will go to the cursor 2, I will change it to minus 4.6, right. So, here we can observe that when the input signal is greater than this yellow line, the first yellow line, right, the output is becoming minus VCC, whereas when the input is lower than second cursor line, it is going to plus VCC. Yeah, we can see here when the input is greater than plus VCC, sorry, first cursor line which is 4.6, then the output is minus VCC, and when the input is lower than minus 4.6, this particular yellow line, the bottom yellow line, the output has become plus VCC, right. So, when we verified, both the theoretical, practical as well as simulation got the same thing. I hope you understand the practical applications of the Smith trigger as well as how to do the connections and how to verify the working of the Smith trigger, inverting type of Smith trigger. In next module, we will discuss about non-inverting type of Smith trigger. Thank you.